A key part of the course is thermistors, which have a charge carrier density and a changing resistance. Now, this is a typical resistance temperature graph for what's known as an NTC thermistor. That is a negative temperature coefficient thermistor. So you can see as the temperature rises, then the resistance falls. So it has an inverse relationship. So here's the point. For an NTC thermistor, as the temperature rises, the resistance of the component falls. But the real key question is, why? And that is what you often have to answer. And we do it by following a series of logical steps. What you need to do is identify the change. So it might be as the temperature rises. Now, once you've identified what that change is, you then need to identify what is the consequence of that change. Then that consequence will become the next change with a follow-on consequence. So it becomes a logical chain of events. Just to take thermistors. Thermistors are made of a semiconductor material. Now, the charge carriers in electricity are electrons. To keep it simple, we're not going to go into quantum physics and discrete energy levels, but in simple terms, we describe electrons as either being in the valence band, that means attached to the ion and unable to move around, or they're in the conduction band, having left the actual atom. Now, in semiconductors, the energy levels between the valence and the conduction band are very, very close. It doesn't require huge amounts of energy to jump from the valence to the conduction. So small increases in energy can release a significant amount of electrons from the valence to the conduction band. At room temperature, most electrons are in the valence band. And we say it has a low density of charge carriers, the charge carrier density, which we show as N. What it means for a specific volume, its amount of electrons for that volume is very low. Now, we're talking about huge numbers per cubic meter. Now, I obviously are just showing a few atoms and electrons. I'm showing a simple atom with 3 outer electrons. It could be 4, 5, 6. It's not really important. And I'm not talking about the type of bonding either. But what it's to help us show is, in this case, the conduction electrons shown in red are quite small in number. Now, here's the point. As the temperature rises, ions now have increased kinetic energy, because our temperature is the average kinetic energy per molecule. Now, some of this energy transfers to electrons, and in many cases, it's enough or the correct amount for them to transfer to the conduction band. As I now show, far more for the same volume, think of it 3D, far more red conduction electrons compared with the earlier cooler temperature. Now, it's important to note that if you have an EMF or a potential difference, you have about the same electric field. Same electric field, which is a year 2 topic, means the same force on each charge carrier. And it will be in the direction of the positive terminal, as I show it all to the left. Now, that similar force or same force will give about the same drift velocity. And this force would also balance with the resistive force that comes from collisions. And with the same temperature, you'd have the same amplitude of lattice vibration. Now, let's show this a little bit more accurately. So imagine you've got, I'm showing it's 2D, but I want you to imagine it's 3D with a cross-sectional area A. And I'm interested in a length D. Now, just to let you know, Q is the charge per each charge carrier. So that's going to be the elemental charge, because they're electrons. I'm showing the electrons in red, that's conduction. And I'm just showing the atoms, or what they would actually be as the lattice ions, in blue. N, again, it's the charge carrier, the density. How many do we have in a given volume? And Q is the total charge in this given area or given volume, which would be the length times the cross-sectional area. And T is going to be the time it takes for that amount of charge on average to drift towards the positive terminal. So this is what it's more likely to look like. Random motion, where over time, and over a time t, we actually move or drift on average to the left. Now, we're going to use that to the transport equation. Now, I want you to imagine in that given volume, you would have a certain amount of charge, and that charge Q is going to be equal to the charge carrier density times the volume. That will give you the number of charge carriers, but we must multiply it by the charge per each charge carrier to get the total amount of charge in coulombs. Now, as I think you can clearly see, the actual volume could be expressed as the cross-sectional area A times the distance d. Now, what we've got is we've got a drift, haven't we? And how would we show that drift? And how would we also understand current? Because current is the charge passing a point per unit time. So imagine we have a time t, and in time t, that travels, on average, drifts a distance d. So what would we get? We would end up getting q divided by t and d divided by t. What would that be? Well, charge per unit time is the current, and distance traveled in a time t is the drift velocity. So we end up with the transport equation, which is that the current is equal to the charge carrier density, times the cross-sectional area times the drift velocity times the charge on each charge carrier. Now here's the important point. If the wire has a constant cross-sectional area, and because you've got the same potential difference, you have the same V, and Q is constant because it's the electron charge or the elemental charge, then from this equation we can make the direct point that the current is directly proportional to the charge carrier density. Therefore, the next point comes with Ohm's law, which, if we use it in terms of resistance, is the potential difference divided by the current. If V is constant, as we've set it, then simply R is inversely proportional to the current. So step by step, 1. Increased temperature, consequence, increased charge carrier density. Step 2. Increased charge carrier density, consequence, increased current, as current is directly proportional to N. Finally, increased current, according to Ohm's law, decreased resistance. So what do we get? We get the key point. For a negative temperature coefficient thermistor, as the temperature rises, the resistance of the component falls.